When formulating where conditions, you mainly compared single values and evaluated selection tables, that is, select options. The comparison values here were data objects, that is, variables and literals. However, OpenSQL also supports a variety of operators and enables you to compare database table fields with one another. The figure illustrates an example of a complex search for airline customers using name and address data. The underscore and %sign placeholders correspond to the SQL standard in delimitation with like. In other ABAP statements, the plus and asterisk characters are used for similar comparisons, for example, within comparison tables. To search for the underscore or %sign characters, use the escape addition to define an escape symbol. A condition that the column contents must contain an underscore in any location is then formulated as like %sign exclamation mark underscore %sign escape exclamation mark. When the developer links conditions, the AND operators are evaluated before the OR operators. Set parentheses to change this order as needed. Note, the selection of the operator can have a major impact on the usability of a condition for an index search string. The formulation of the where condition influences the search strategy of the optimizer and the performance of the database access.
In addition to variables and constants, you can also enter fields from the same database tables after the comparison operators, for example, equal to EQ, not equal to NE, less than LT, in the where conditions of OpenSQL statements. Entering fields from the same database tables after the comparison operators makes it possible to compare two database fields with each other in the where condition and only read the records whose contents fulfill the condition. To avoid the confusion of the second table field with the data object, the name of the database table must be specified with a field label connected with the tilde character. Alternatively, use an alias for the table name, which you define with the AS addition after the table name in the from clause. Aliases for table names play a subordinate role here. They are used to abbreviate the where condition. However, you see aliases again in the formulation of joins, where they are crucial if the same database table appears several times in the from clause. Caution: the fields that are compared must have the same basic type and length. Ideally, they are based on the same domain. Otherwise, the result depends on how the respective database system stores the different types and how it handles spaces at the end of values.
When you specify data objects as targets of select statements, you need to differentiate whether the target area that is specified after info is single line or multi-line.
Single-line target areas are used for single record access using select single and in single loops using select and select. The target may be a structure, that is, structured data object, and is always specified with the into addition, without table, or with into corresponding fields of. You can also specify a list of elementary data objects or elementary structure components. In this case, the individual fields are separated by commas, while the entire list is enclosed in parentheses. The syntax of this value is correct only if there are no spaces between the open parenthesis and the first data object. Any number of spaces can appear before the closing parenthesis, before and after commas, but are not required. Specifying individual structure components is a more robust alternative to specifying the entire structure after the corresponding fields of addition. In theory, you can also specify a list of individual data objects and structure components after into corresponding fields of.
When select statements have multi-line target areas, you must specify an internal table as the data object. Specify the table, for example, after the into table addition or after into corresponding fields of table. Alternatively, replace into table and into corresponding fields of table with appending table and appending corresponding fields of table respectively. If you use into, the contents of the internal table are replaced completely with the selected data. If you use append, the data is added to any existing lines in the table. Hint: if you use appending for sorted and hashed tables, no append is performed. Specifically, the addition is not treated as an index access to the internal table, which means it can also be used for hashed tables. In sorted tables, the new lines are inserted in the existing lines in accordance with the sort sequence.
A disadvantage of sequential processing in the select loop is the fact that only one record is available to the application log at a time. The availability of a record is particularly problematic when you want to change the records in the database because the changes can only be carried out by single record access. However, a large number of single record write accesses have a negative impact on the database and program performance. For such cases, OpenSQL provides a variant of the select statement in which the data is processed in a loop, that is, select and select, but the target area is multi-line, that is, into table. The number of records that are placed in the internal table at the same time and processed in the current loop pass is defined with the packet size addition. You can specify this number either statically or dynamically, but it is defined once at the start of the loop. The same number of lines are processed during each loop pass. Packages of different sizes can be processed sequentially with the syntax illustrated in the figure. In this variant of database read access, the access itself is detached from the transfer of the result set to the application program. The open cursor statement defines and executes the access, but does not pass any data onto the application program. The fetch next cursor statement retrieves the desired number of lines, that is, packet size addition, from the result set and copies them to an internal table. The close cursor statement completes the database access. After open cursor, the cursor variable points to a position before the first line. The sequential fetch statements not only allow you to read different numbers of records, but also allow you to specify a different data object as the target, such as structures or internal tables after each into.
In OpenSQL, you can have the database sort the dataset by specific criteria directly as part of the select operation. To do so, use the order by clause for the select statement. In the simplest form of the order by primary key clause, the table is sorted by its complete primary key in ascending order. To use order by primary key, the prerequisites are as follows. The from clause contains a single database table with no views or joins. The field list after select contains all the key fields of the table, including the client, which is often forgotten. The syntax order by COL1, COL2 sorts the data by any existing columns. The sequence of the specified columns determines their sort priority.
The figure shows an example of the order by addition with free column selection. If you do not use an addition, the system sorts retrieved datasets in ascending order. You can use the optional descending and ascending clauses after a given field to define the sort direction. Note, sorting can be a computationally expensive process if the result set is large and the sort fields are not also index fields.
The select distinct statement in OpenSQL instructs the database to aggregate the result set of a select statement, such that it does not contain any duplicate entries. All fields of the result set are used for the comparison. You can either load the result of select distinct into an internal table, that is array fetch, or process it sequentially, that is select loop. For select distinct, the applicable restrictions are as follows. The field list cannot contain any columns with type LCHAR, LRAW, string, or raw string. You must use select distinct asterisk to access pooled tables and cluster tables. You cannot select individual columns.
When an into clause is used with aggregate expressions, the data object in the into clause must provide a structure component or table column with the appropriate type for each aggregate expression in the select statement. When aggregate functions are used, there is a major difference between cases in which the field list consists exclusively of aggregate expressions and cases in which the field list also contains field labels that are not arguments to an aggregate function.
If the field list in a select statement contains only aggregate expressions, the result contains a single line. A structure may be specified as the target if an into clause is used, similar to the select single statement. The figure illustrates an example. Hint, if the field list only contains the minimum, maximum, sum, and average functions, but not count, an internal table can also be specified as the target. Because the result is a single line, only the first line of the internal table is filled.
In addition to count, asterisk, the count function is used in combination with a distinct clause in the form count distinct COL. This aggregate expression returns the number of unique, distinct values in the specified column. You can use the distinct addition for all other aggregate functions as well. For example, AVG, distinct COL. Values that occur multiple times in the column in the selection result are only included once in the aggregate calculation. The table is retrieved before the aggregate is calculated. Note, in the example, the aggregate sum, distinct seats occupied, is only intended as an illustration, not as a typical example of the technique. In general, the distinct clause is most useful when applied together with the count function and is not commonly combined with the minimum, maximum, sum, and average functions. When writing select statements that consist only of aggregate expressions, keep in mind the following considerations.
If the field list of a select statement contains field labels in addition to aggregate expressions, the result is always multi-line. As a result, it must be loaded into an internal table, that is, array fetch processed sequentially, that is, select loop. The select statement must contain the group by clause and all fields that are not arguments of an aggregate function in the field list must be listed after the group by clause. When the group by clause is specified, the database does not apply the aggregate functions to all the retrieved records together, but instead sorts them into groups first. A group contains all the records that have the same contents in the columns specified after group by. The aggregate functions are evaluated separately for each of these groups. Each group then corresponds to one line in the selection result. When you use group by, you can specify a logical expression after the having expression to restrict the result set further. In contrast to the where condition, the logical expression after having can also contain aggregate functions in SAP Web AS 6.10 and later. Apart from the aggregate functions, the logical expression after having can only contain fields that are specified after group by. If you use field labels after having that are not listed after group by, this does not cause a syntax error, but results in a catchable runtime error, that is cx_sy_open_SQL_db. The aggregate functions after having are different from the aggregate functions after select. In the example, you could specify a condition count asterisk greater than 1 after having to only evaluate groups that contain more than one flight. You do not have to use the aggregate count asterisk function after select in this case.
In a relational database system, such as OpenSQL, attempts to access data stored in a primary table require reads from the associated secondary tables as well. The obvious programmatic method to perform those accesses is to loop over the records in the primary table with nested selects. However, secondary tables may themselves have associated tables that need to be read in turn. There is no theoretical or practical limit to the nesting depth. The nested select model can indefinitely chain tables as long as the tables are linked by common data columns. For a number of reasons, nested selects are the most resource-intensive method possible for reading multiple linked database tables, and good program design will avoid this method for any but the smallest and simplest of data access procedures. Nested selects place a high load on the database server and produce large amounts of network traffic, because many partially filled data packages are transferred and the same data may be read many times in a row, that is, identical accesses. In this lesson, you will learn several techniques that enable you to largely avoid nested selects and to reduce their negative impact on system performance when their use is unavoidable.
To read data that is distributed across multiple tables, you must create a link between the functionally dependent tables. The link between the tables is known technically as a join, and the corresponding database operator is join. To implement a join, you can use either database views in the ABAP dictionary or ABAP joins. Database views and ABAP joins can only be used with transparent tables. If you are working with pooled tables or cluster tables, you have to use other techniques. You can derive the logic of the inner join and outer join from the intended result set. An inner join produces the result set that only considers the records from the outer table for which suitable data records exist in the inner table, as in the example. A left outer join produces the result set that contains all the records from the outer table, regardless of whether or not suitable records exist in the inner table. If no suitable records exist in the inner table, the fields of the inner table, that is, the other table, that is used in the left outer join condition, are set to 0 values in the result set. The tables involved in a join are called base tables. A projection or column selection or a selection or line selection can be applied on the result of a join. Not all of the databases supported by SAP support the standard syntax for on conditions. Therefore, use restricted syntax to ensure that only joins that return the same result set on all database systems are allowed. A disadvantage of using ABAP joins is that the statement is more complex than a dictionary view, where the syntax of the select statement, specifically the from clause, corresponds to a regular table access. Hint: note that ABAP joins always bypass the table buffer, which is only a disadvantage for joins involving buffered tables. Dictionary views can be buffered in SAP R3 Release 4.0 and later, depending on which tables are used in the view.
Attributes and benefits of database views are as follows.
A subquery is a query within a select, update, or delete statement. It is formulated in the where or having clause to check whether the data in various database tables or views possess certain attributes. A select statement with a subquery has a more restricted syntax than a select statement without a subquery. If the subquery returns exactly one value, use the usual comparison operators apart from like and between. If you use a subquery with a comparison operator instead of with exists, then the select clause of the subquery can only contain a single column, which can be a field in the database table or an aggregate expression. In this example, the subquery is supposed to return several lines, each with one value. If you want to compare all the returned values, use in. Subqueries whose where condition contains fields from the main query are called correlated subqueries. If subqueries are nested, each subquery can use all the fields from the higher level subqueries in the hierarchy. Query designers should formulate positive subqueries whenever possible. Negative formulations may result in performance degrading database reads if no adequate index is available. Hint: in many cases, you can also use a join to obtain the same result as that produced with a subquery. The SQL code for a join is easier for other developers to read and understand, but no blanket statements can be made about the relative performance of subqueries and joins, as the table design, query logic, and amount of data to be retrieved all can have major impacts on the performance of both methods. For performance-critical systems, it is advisable to prototype the query using each method and running performance profiles with real-world data to ascertain which approach will produce faster output.
You know how to use the Open SQL statements Open Cursor, Fetch Next Cursor, and Close Cursor to program explicit cursor handling. You also know how cursors are opened in several database tables at the same time. This knowledge enables you to process the contents of multiple database tables in parallel without using nested selects. You want the program to process all flights from database table S flight, and you want to read the non-cancelled bookings in the economy class for each flight from database table S book and process the bookings together with the flight. The obvious solution is a nested select, but that solution is likely to perform slowly. Due to the large data volume involved, do not buffer the bookings completely in an internal table. Rather than solving the problem with nested selects, you can achieve the same result by addressing the two database tables with two concurrently open database cursors. See Figure 196. For this technique to work correctly, the table and record design need to fulfill the following prerequisites. Both tables must be sorted by the same criteria, that is, order by clause. Every record in the outer table must specify exactly and correctly how many corresponding records exist in the inner table. If these conditions for the data are not met, then the concurrent cursor program design will return incorrect results or fail to work at all. It is therefore a less robust, though much better performing approach to the problem. Hint: To circumvent the second criterion and improve the robustness of the solution, you can open two cursors for the same database table and have the outer cursor use the count * aggregate function to determine the number of records in each group.
In many cases, the application logic does not permit the use of joins. If you need to read data from multiple tables in such cases, you can use a separate internal table to buffer the read data.
In the example, you want to read the matching data from S-Travel AG, that is, Travel Agency Master Data, within a loop for the bookings from table S-Book. Accomplish this with a select single statement or a read routine. If you use select single in this approach, execute identical SQL statements. Therefore, encapsulate the reading of S-Travel AG records in a read routine. In the example, the table contents read from S-Travel AG are buffered in a static internal table. Before each database access, the system checks whether the corresponding table entry has already been read. The read routine can also be a method of a local or global class instead of a subroutine. In this case, a private attribute of the corresponding class is used as buffer instead of the static internal table st_travel AGS.
Select for all entries was created in OpenSQL at a time when it was not possible to perform database joins. This was not supported for all SAP-approved DBMS. The connection between the inner and outer database tables was created in ABAP. Nowadays, this technique is often used when some data is already available in an internal table, but additional data is to be read from the database. In such cases, select for all entries replaces a select single statement inside a loop over the internal table and normally shows better performance than such a loop. The content of the internal table or driving table is used as a restriction for the database access and may depend on the database system. In general, the database interface takes a certain number of entries in the internal table. In the example, it takes 5 and sends one native SQL statement to the database for each group. In the end, the results of the individual native SQL statements are combined to form the result of the OpenSQL statement. Duplicate entries are automatically removed. Note that the size of the packages is controlled by a profile parameter.